This is our first problem in the velocity analysis, the relative velocity analysis. We could have actually tackled this problem by using the absolute analysis. What we could have done is we could have assigned a frame around a fixed location, and that would be our inertial frame. And then with respect to this inertial frame, then we can define this motion of A similar to the problem that we had for the absolute analysis. And then the amount of angle that has been elapsed is 90 degrees here. So theta would be equal to 90 degrees. And we would find a solution by the absolute analysis. However, since our subject is on relative velocity, we're going to tackle this problem by using the relative velocity analysis. So I'm just going to get rid of these drawings. And here what we need to do is we need to place a frame that is fixed to the rigid body. And the rigid body is a tire here, the wheel of a car. And this is an assumption, by the way. The tire is never in this shape. There's a flat region here, but this is our assumption. It is perfectly circular. And then the other assumption is that the wheel rolls without slipping. With respect to these assumptions, now there is this information of V0. The V0 is the speed, the velocity of the car. So this wheel's mass center is moving at a V0 speed. However, as the wheel rotates, any other point on the wheel would have a relative velocity with respect to this mass center O. And that will be defined by using the angular velocity information. So we could have written this equation here as it's shown. VA, the velocity of A point, is equal to the velocity of O point, this point, plus the relative velocity of A with respect to O. Now, if we have defined our axes as X and Y axes in this way, the Y-axis is upward, X-axis in the horizontal, then the Z-axis is the axis that is going out of this page. Z-axis is going out of the page. We determine that by using this type of representation usually. This means the vector is going out of the board. If you see an X inside, that means the vector is going inside the board. Now this is the situation. The Z-axis is going out of the board. So with respect to our right-hand rule, the velocity of this angular velocity of this wheel, the direction is in this direction, and with respect to the right-hand rule, this is a negative direction. How do you understand that? Place your thumb in the direction that is going out of the board, and to your palm, the rotation to your palm, inside of the palm, is a positive rotation, but this omega is to the back of your hand. Therefore, this is a negative rotation. So I can define this omega vector as a negative omega k, k being the unit vector defined for the z-axis direction. Okay, or negative omega k. We can solve this problem by using the vectors, or you can find a solution quite easily because this is an easy problem. You can already say that, well, the relative velocity of point A with respect to O is r omega. It is in the upward direction. Sorry, it will be in the upward direction in this way, and r omega is actually equal to V0. So I can find the solution if the absolute velocity of A point is given to me as 12 meters per second. That means 12 is equal to the square root of V0. The magnitude of the absolute velocity of point A on the mobile platform. Okay, mobile automobile tire is 12 meters per second. So this is V0 squared, oops, v0 squared plus r omega squared, which is basically equal to v0. So this is v0 squared as well. Or in short, this is just the square root of 2 times v0 squared. And then you can find the solution. Now, you can find a solution to find the magnitude of A, and then you can calculate V0. If you calculate V0, R is known, so you can calculate omega. Or we can make use of the vector calculation, and this is my recommendation. This is an easy problem. You can get away with just these type of inspections and then find the solution, but I would strongly recommend that you use these vector notations. So with respect to this vector rotation, the equation turns out to be the V0 vector, and this is in the x direction. So you can call this V0 as, by the way, V0 I. Okay, so this is in the I direction. And then the relative velocity will be calculated as omega vector cross product, actually, the distance vector from O to A, or you can write it out as A with respect to O. Okay, this is another vector. And this, well, this is already written out here, but I could have also written this out as ROA, from O to A. The same type of information written out in a different way, or OA vector itself. Now, OA vector with respect to our definition of the frame is in the negative direction of the x direction. So that will be equal to negative Ri. And R is already available to us. Diameter is given to us as 650. So the half of that would be the R magnitude. Anyways, so as a result of that, if you do this calculation, omega k cross product R OJ RA with respect to O, and this is calculated as negative RI. Cross product of K with I is J. Negatives cancelled out each other, so as a result of that, we get this component omega RJ, and then V0 is V0I, and V0 is calculated by R omega, so this is that part. And this composes the velocity vector of a point. Now the magnitude is given to us, so we need to take the squares of all these components, add them up, and then that will give us the velocity, magnitude of the velocity of point A. From this 12, knowing the value of R as the half of 650, 325 millimeters, then we are able to calculate the speed of this angular speed of this tire, and also you can calculate the velocity of the car.